Welcome to the lecture on addition and elimination reactions, part 5. In this module, we are going to discuss about the mechanisms and applications of Perkin, Stobbe and Benzoin condensations along with Mannich reaction. We shall start with Perkin's reaction. Perkin's reaction is an aldol condensation of an organic acid anhydride with an aromatic aldehyde to give an alpha beta unsaturated aromatic acid. This reaction involves three major steps. The first step is under the influence of a base, the acid anhydride generates an enolizable carbanion. This enolizable carbanion attacks the carbonyl carbon of the aldehyde. This attack yields an intermediate, and this intermediate further reacts with one more molecule of acid anhydride to generate a new intermediate. And this is the first step. In the second step, an E2 elimination reaction takes place. A hydroxide base is used for removal of a proton from active methylene group, and that is followed by elimination of a carboxylate ion to generate an unsaturated anhydride. The resulting anhydride product is hydrolyzed finally to generate an alpha beta unsaturated acid. So we shall once again discuss the mechanism in detail. This is an acid anhydride. Here I have taken acetic anhydride. With that I am adding sodium acetate as the base. So this acetate ion, the base, is removing the most acidic hydrogen of the molecule, the alpha hydrogen, generating a carbanion here. So after the removal of this hydrogen as proton, we will have a minus on carbon here. That minus moves here to form an enolate. This enolate ion is reacting with an aldehyde, generating a new intermediate. And this intermediate ion, which is an alkoxide anion, is attacking the acid anhydride part, the carbonyl group of an acid anhydride part. It is attacking at the carbonyl group, pushing this bond to oxygen, resulting in a cyclic species. And here the minus comes back and pushing this bond with oxygen, resulting with a new anion. And this anion, in this reaction we can see this oxygen has taken up this acetyl group with that. So this oxygen has now taken up the acetyl part, and this part has gone out as carboxylate ion. And this carboxylate ion is once again reacting with another molecule of acid anhydride and getting acylated. An acetyl group joins with O minus to generate a new acid anhydride. So this is the new intermediate we have got. We are adding a strong base to carry out an E2 elimination. So this is an active methylene group here. When we add a strong base, it removes the hydrogen from active methylene. The acidic hydrogen is removed. As the hydrogen is removed, these bonded electrons move here and pushing out an acetate ion from here. So a H plus from here and an acetate ion here from here are removed simultaneously. So this is an E2 elimination. So after the E2 elimination, we have an unsaturated acid anhydride. Now we are once again hydrolyzing this anhydride part with the same hydroxide base, that results, so this hydroxide attacks here and it goes out as acetic acid, and this side we have O minus. So that acetic acid gives up a proton from this proton to this carboxylate ion to form alpha beta unsaturated acid. Here are few examples for Perkin's reaction. Here I have taken an aromatic aldehyde and I am treating it with a anhydride, acid anhydride. This is acetic anhydride, and it is treated with potassium acetate, the base. So aromatic aldehyde, acid anhydride, under the influence of a base generates an intermediate, and it is treated with a strong base for E2 elimination and then for hydrolysis to give an alpha beta unsaturated acid. So the conversion is very clear. The aldehyde part, the carbonyl group, is now made into carbon olefinic double bond which is connected to a carboxyl group. So the aldehyde group is replaced by an alpha beta unsaturated acid group. So here is another example. I have taken an aromatic aldehyde and an acid anhydride. Under the influence of a base, the Perkin's reaction will take place to form an intermediate, and that after E2 elimination followed by hydrolysis of the resulting anhydride, we get an alpha beta unsaturated acid, aromatic acid. So here also what we find is the carbonyl group of the aldehyde is now converted to an olefinic double bond, and which is connected to a carboxyl group. So if you want to connect an alpha beta unsaturated acid group with an aromatic ring, we can start with an aromatic aldehyde and we can carry out Perkin's reaction with acetic anhydride in basic medium. Condensation of diethyl succinate or its derivative with a carbonyl compound in the presence of a base is called Stobbe condensation. Diethyl succinate or its derivative is treated with a carbonyl compound in the presence of a base. So diethyl succinate on treatment with a base generates an enolate ion. That enolate ion reacts with the carbonyl group of the ketone, resulting in the formation of an unsaturated acid. Here is the mechanism for Stobbe condensation. This is a diethyl succinate. With that we are adding sodium ethoxide as base, and this base is removing or abstracting a proton from alpha hydrogen, the most acidic hydrogen of this molecule, resulting in the formation of a carbanion, and this carbanion is an enolizable carbanion. So this minus makes a double bond here, and this pi bond is broken to give the enolate, and this enolate ion once again can regenerate the carbanion. This carbanion is attacking the carbonyl carbon of the ketone, resulting in the formation of a new alkoxide. So this carbon with minus charge is attacking the carbonyl carbon of the ketone. So when minus makes a bond with the carbonyl carbon, the carbonyl pi bond breaks to give O minus, that is the new alkoxide. And this new alkoxide I have shown here. Here the O minus is nearer to the carbonyl group of another ester group. Therefore, This O minus as nucleophile attacks at the carbonyl carbon, generate resulting in the formation of a new anion. So O minus attacks at the carbonyl carbon, making a new bond, and this pi bond is shifted to oxygen to give O minus. That O minus comes back to regenerate the double bond, pushing this ethoxide out. So this overall reaction is a nucleophilic substitution at this carbonyl group. So this is the nucleophile attacking the carbonyl carbon. Ethoxide is the leaving group. Therefore, this is a nucleophilic substitution, and the ethoxide is the leaving group and it is removed. So finally we get a new product. So the ethoxide ion that has gone out is once again reacting with this molecule. It removes the most acidic hydrogen of this molecule, the alpha hydrogen from this is the ester, carbonyl group of ester, and this is alpha carbon. So from this alpha carbon, this ethoxide abstracts a proton, resulting in the formation of carbanion. And that carbanion makes a bond here, pushing this out as carboxylate. So this is similar to an E2 elimination. The base removes a proton from here, and the negative charge, after the removal of proton, you will have negative charge. That negative charge makes a bond, and that pushes out the carboxylate. So H plus from here, O minus from here are removed by the base, strong base. Therefore this is an E2 elimination reaction. So by the E2 elimination we are ending up with an olefinic double bond. So with this olefinic double bond we have a carboxylate ion that takes up a proton from ethanol in the medium and gets protonated. Therefore the carboxylate ion is protonated here and we have a new double bond, and this is the product of Stobbe condensation. So in the overall reaction we can see the carbonyl carbon of the ketone and the alpha carbon of the succinate, diethyl succinate, are connected by a double bond, and that is the product of Stobbe condensation. We use diethyl succinate and a ketone. The carbonyl carbon of the ketone and the alpha carbon of the ester, succinate ester, they are connected by a olefinic double bond, and that is the product. The Stobbe condensation is used for the extension of aromatic rings. In this reaction I start with an aromatic ketone and we are treating it with diethyl succinate ester in the presence of an alkoxide base, and by Stobbe condensation we end up with this product. An aromatic ketone reacts with diethyl succinate in the presence of a base to give this product. As I said earlier, in this Stobbe condensation a new olefinic bond is generated between the carbonyl carbon of ketone and alpha carbon of diethyl succinate. So with this Stobbe condensation is over, and further what we are doing here is we are converting this acid into acid chloride by treating it with thionyl chloride. So it will become, on treatment with thionyl chloride, this COOH will become COCl, an acyl chloride. Now we can add a Lewis acid. In the presence of Lewis acid, an acid chloride part will react with the aromatic ring, and that reaction we call as Friedel-Crafts acylation. So for Friedel-Crafts acylation, the carbonyl group is connected to the aromatic ring. Now, by adding sodium borohydride in alcohol, we can reduce this carbonyl to alcohol. So this is sodium borohydride reduction or hydride reduction of carbonyl group to alcohol. So this on dehydration generates a new double bond here. Therefore, we have generated a new aromatic ring. Therefore, Stobbe condensation can be used for the extension of aromatic rings in aromatic ketones. Benzoin condensation. So the benzoin condensation is a reaction between two aromatic aldehydes, usually benzaldehyde or its derivatives. This reaction is catalyzed by cyanide ion, and the reaction product is an aromatic acyloin. Acyloin is nothing but alpha hydroxy ketone. Alpha hydroxy ketones are called acyloins. So here we get, in this reaction we get alpha hydroxy ketone, we call it acyloin. Since it is derived from benzaldehyde, it is called benzoin. So in benzoin condensation, we start with benzaldehyde or its derivatives, and we end up with benzoin or substituted benzoin. The mechanism of benzoin condensation is given here. We start with benzaldehyde. With that we add cyanide. This cyanide is attacking at the carbonyl carbon, shifting this pi bond to oxygen. So we get O minus here. The nucleophilic anion has attacked carbonyl carbon, shifted the pi bond to oxygen. So this O minus takes up a proton from water to become a cyanohydrin. The hydroxide generated here is removing the proton from here. So this proton is acidic because in one side it has an electron withdrawing oxygen, and in the other side an electron withdrawing cyano group. Therefore this hydrogen is acidic. So this acidic proton is removed by the hydroxide base. Once H plus is removed, this carb anion undergoes rearrangement. So this minus charge is making a pi bond here, and this pi bond is shifted to N minus. So the negative end is shifted from carbon to nitrogen. There is reversal of charge. We had C minus here after the removal of H plus. That minus is now shifted to nitrogen. Now once again the minus charge comes back to the carbon, attacking another molecule of benzaldehyde, the carbonyl group of another benzaldehyde. So the minus comes back here, and this pi bond is shifted to carbon. So once again carbon becomes carbanion. It is becoming a nucleophile. It is attacking the carbonyl carbon of another benzaldehyde, and where it is making a new bond. When a new bond is made here, the pi bond is shifted to oxygen, and that becomes O minus here. That O minus takes up a proton from another water molecule, and we get a product which is less stable. This is cyanohydrin, which reacts with the hydroxide generated from here. That hydroxide takes up a proton from OH, therefore it becomes O minus. So O minus is pushing out the cyanide. So a nucleophilic substitution is taking place at this carbon, where O minus is the nucleophile, cyanide ion is the leaving group. Therefore, we end up with a carbonyl group. So we get an alpha hydroxy carbonyl compound, an acyloin. This acyloin alpha hydroxy ketone obtained from benzaldehyde or benzaldehyde derivatives are called, the one obtained from benzaldehyde is called benzoin, and all other derivatives of this benzoin are also called benzoins. Another very important reaction is Mannich reaction. In this Mannich reaction, we take up a carbonyl compound with alpha hydrogen. This alpha hydrogen is replaced by an amino alkyl group in Mannich reaction. For this, we use ammonia, primary amine or secondary amine. We add it with formaldehyde in the presence of organic acid, and these two in the presence of organic acid generate an electropile, and that electropile is reacting with this substrate, resulting in the formation of amino alkyl substituted carbonyl compound. Mannich reaction, we use an amine with formaldehyde. We can use ammonia or a primary or secondary amine with formaldehyde in the presence of an organic acid. This mixture generates an electropile, which is an iminium ion, and for this process we should not use tertiary amine as it has no hydrogen connected with nitrogen. And along with this, we add a carbonyl compound with alpha hydrogen. So this alpha hydrogen of carbonyl compound is acidic. So we, in this reaction, as I said, we can use carbonyl compounds, and the carbonyl compound can be replaced by nitriles, acetylenes, aliphatic nitro compounds, alpha alkyl pyridines, and so many other molecules. Even it can be used with activated phenyl groups. The mechanism of Mannich reaction is explained here with an example. Here I have taken cyclohexanone, dimethylamine, a secondary amine, and formaldehyde as its aqueous solution in the presence of a catalytic quantity of hydrogen chloride, hydrochloric acid, to form an amino ketone as product. So earlier, as I said, we have to use an organic acid with amine and formaldehyde. Instead of organic amine, we can use very small amount or catalytic quantity of a mineral acid also. So in this reaction, we start with cyclohexanone. We add N-dimethylamine, formaldehyde, very small amount of hydrogen chloride or hydrochloric acid. First of all, the dimethylamine is reacting with formaldehyde as I have shown here. So the amine in Mannich reaction, this amine may be ammonia, primary amine or secondary amine. In this reaction we have taken a secondary amine. So this behaves as a nucleophile. So nitrogen has got a lone pair, therefore it behaves as a nucleophile. So with its lone pair it attacks the electrophilic carbonyl carbon, and this pi bond is shifted to oxygen to give O minus. So here either by proton transfer from here or by taking up a proton from the acid, the O minus gets protonated. Suppose if it is protonated from acid, nitrogen is still holding positive charge. Therefore, this hydrogen will be removed as a proton. That proton will protonate this OH group. Therefore, the OH is protonated here to form oxonium ion, which is a very good leaving group. Therefore, the nucleophilic nitrogen with its lone pair makes a bond here and replaces a water molecule. A nucleophilic substitution takes place here where nitrogen with its lone pair is nucleophile, water is the leaving group. It results in the formation of an iminium ion. This iminium ion is an electrophile. Now the second part of the reaction, we have cyclohexanone as substrate that in the acidic environment undergoes enolization by keto-enol tautomerism. So this is ketone and it forms and it's enol in acidic environment. And this enol reacts with the iminium ion. So this OH bond is broken, H plus is removed. So this bond is shifted to make a double bond here, and this double bond is shifted to alpha carbon to give a minus. That minus attacks the electrophilic carbon of iminium ion. So a new bond is made between alpha carbon of the carbonyl carbon and the carbon of iminium ion. As a new bond is made here, this bond is shifted to nitrogen, and that is how we get amino methyl derivative of cyclohexanone. This is an amino group, NN dimethyl amino methyl cyclohexanone, and this is how we are introducing amino methyl group into alpha carbon of the carbonyl compound, and instead of the carbonyl group, as I said earlier, in this place we can have some other strong electron withdrawing groups. In Mannich reaction, we end up with amino methyl carbonyl compound. So in the example I gave you, we started with cyclohexanone and we ended up with NN dimethyl amino methyl cyclohexanone. So the product of Mannich reaction is amino methyl carbonyl, and maybe in the carbon instead of carbonyl there may be some other electron withdrawing groups. Mostly the Mannich reactions are carried out with carbonyl compounds. So the product of Mannich reaction is alpha amino methyl carbonyl compound, and this amino methyl compound can be treated with methyl iodide. So this may be here it is NN dimethyl amino group. It may be a simple amino group like NH2 or NH methyl or NN dialkyl amino group like this. So the amino group on treatment with excess of methyl iodide, it undergoes methylation. So here nitrogen has a lone pair, it behaves as nucleophile, attacks the carbon of methyl, replacing iodide by SN2 mechanism. So all the hydrogens of amino group will be replaced by methyl, and finally lone pair will react with another methyl iodide to form a quaternary ammonium iodide, a quaternary ammonium salt. And with this salt we add a hydroxide base, and this hydroxide base abstracts the alpha hydrogen the most acidic hydrogen of the molecule, leaving a carbanion behind. It forms the conjugate base of this molecule. So the hydroxide removes proton from here and the resulting species is carbanion, the conjugate base of this molecule. And that carbanion with negative charge makes a bond here, pushing this into the pi bond into oxygen. So we end up with enolate. So the minus comes back and the pi bond is shifted here, pushing out the good leaving group, quaternary ammonium ion, resulting in the formation of a new double bond. So the product of the Mannich reaction can be treated with the excess of methyl iodide. We can end up with quaternary ammonium salt that is treated with a strong base that results in the conjugate base. Therefore we call this mechanism as E1CB mechanism, unimolecular elimination through conjugate base mechanism. So the base removes a proton, leaving the conjugate base C minus. That carbanion is enolizable, resulting in the formation of enolate. That enolate is pushing out the good leaving group, the quaternary ammonium ion. It results in the formation of an hexamethylene group here, and this is an enone. So this kind of enones, hexamethylene, enones with hexamethylene are very reactive. So here I have given another example for Mannich reaction, and this is a ketone, and we take up a secondary amine pyrrolidine with formaldehyde and a catalytic quantity of hydrogen chloride. So the secondary amine with formaldehyde in the presence of acid will generate iminium ion. That is the first part of the reaction. And in the second part, the ketone undergoes enolization with acid. So the enol of this carbonyl compound and the iminium ion generated from these two are reacting to form a product like this. And this on excessive methylation with methyl iodide will form quaternary ammonium salt. With that, when we add a strong base, it will result in the formation of Hoffman elimination product. This is also an alpha beta unsaturated carbonyl compound or an enone. I hope you have enjoyed this module. Thank you.